Hello, everyone. Welcome to Topology Optimization webinar. My name is Jun. It's my great pleasure to welcome you on behalf of the organizers at TU Delft and DTU Denmark. Today's session is dedicated to topology optimization for inelastic design. It's organized by Professor Natasha Vermaak from Lehigh University, the United States. Natasha, thank you. The floor is yours.
Thank you. Thank you for the opportunity to highlight these 5 exciting talks from our speakers today that are spotlighting recent publications on this topic of inelastic design and using topology optimization. And we hope to get a lot of feedback and discussion questions from the audience. So please use the chat, question 2, the speaker name, so we know in case there's a transition who your question is for. And they're approximately 12 minutes long with 3 minutes for question. As long as we keep on time, which I'll give people reminders, we will have additional time at the end for some discussion and Q&A as well. So I'm going to introduce our first speaker, Dr. Jasyuk from the University of Illinois at Urbana-Champaign in the US. So if you could share your screen and begin the presentation.
Hi, thank you. Good morning, everyone. I want to thank organizers and in particular thank Natasha for inviting me. Can you see my screen and can you hear me?
Yes.
All right. So I will begin with a brief introduction of my co-authors. So Diab Aboita is Dr. Diab Aboita is my former PhD student. His expertise is in various aspects of computational mechanics. Troy Kang is a recent graduate from the University of Illinois. He was a student of Professor James. Dr. Korik is expert in large-scale computations. Professor Kai James is expert in topology optimization. And my expertise is in micromechanics of materials and materials design. The motivation for this paper is that architectured materials offer possibilities to obtain superior properties. Cellular architectured materials can reach potential to reach superior properties while being lightweight. The properties of such materials depend on base properties, volume fraction, and architecture. One can use various tools to design architecture, and nature can serve as a great guide. There are many structures found in nature that have cellular structures. However, nature optimizes often for several properties and varying loads. So topology optimization offers tools. Is a great platform to design optimal designs for specific properties. The objective of this paper is to design 3D architectured cellular materials with high energy absorption using topology optimization. Our topology optimization problem is a material distribution problem. Our material domain is a unit cell with periodic boundary conditions, on which periodic boundary conditions are applied. Governing equations, equilibrium equations with no body forces and no inertia forces when sigma is Cauchy stress. And as the formulation is in using small deformations theory, so Epsilon strain is infinitesimal strain, and that allows us to decouple elastic and plastic strains. And the problem is displacement controlled with uniaxial strain and shear strain explored as applied loading, and average stress is computed to obtain optimal properties. Elastoplastic finite element method is used, shown here in weak formulation. The noteworthy point is that periodicity is enforced finite elements using Lagrange multipliers as shown here. The constitutive model is elastoplastic model is linear elastic, linear strain hardening. Von Mises yield condition includes linear isotropic hardening modulus, and equivalent strain and initial yield stress is defined here. Strain rates, plastic strain rate, and equivalent plastic strain rates are defined by associated flow rule, and additional two conditions are used to complete the constitutive laws. And here elastic relations are shown. Isotropic for design parameterization, isotropic solid isotropic material penalization method is used. So finite elements are interpolated, material density function P, binary function, and three penalty functions are used, P1 to P3, which allow us to interpolate three material parameters: modulus, yield stress, and hardening parameter. Elastic compliance constraint is also enforced to maintain integrity of design. Three axial strain cases and lower bound and minimum allowable compliance is used since it's a displacement controlled problem. Three axial strain cases are used in the constraints and in the elastic range, and also constraint and value is imposed. And the two objective functions minimized are end compliance and toughness. Toughness is energy absorption, so it's force times, and so it's area under stress strain curve, illustrated here in summation. And since displacement increment is taken as constant, we can express toughness, objective function for toughness in this simpler form. We use path-dependent adjoint method for sensitivity analysis. The objective functions are functions of several variables, and in the adjoint method, augmented objective functional is expressed as follows, where lambda and omega are Lagrange multipliers, and R and H are residuals. For elastoplasticity, these terms are defined as follows, and the other variables are given here. A schematic of our approach is shown here. So we start with initial design, use density filter, use finite element, nonlinear finite element solver, conduct sensitivity analysis using adjoint method, and use optimizer, and then iterate the solution to an optimized design. So in the path-dependent adjoint sensitivity formulation, we have two objective functions. So the derivation is done for each of these functions separately, and the approach involves taking a derivative of this augmented objective functional, using chain rule to account for this dependence on different variables. And there are various steps in the solution. There's not enough time to explain them, but the details are given in the paper. In showing the final some final expressions for toughness and for end compliance. The comment here is that the Lagrange multipliers are obtained starting with m step, and up to the first step. And of course, all these derivatives are computed in the process too, using the input functions as shown earlier. And the numerical results are shown for these specific material constants and 50% porosity. Mesh convergence study was done first. So crude mesh involves 1,000 elements, and then finer meshes. For optimal design, we use 8,000 elements, but to study the effect of initial designs, we used a smaller number of elements. So the results are shown here for optimized toughness and compliance for uniaxial strain. The first column shows the 37 cells for 3 by 3 by 3 configuration. Well, one can see closer detail of each of the unit cell in the images in the second column. The first row represents passive elements assigned close to the center, and then in the second row, passive elements close to the corners, and in the third case, random initial distribution, and a similar for end compliance. So one can see that there are differences in designs due to these initial configurations, and this is also seen in the stress strain curve curves for the 6 cases as summarized here. For the optimized design, we used 8,000 elements, and for uniax, so optimization for uniaxial case, where the uniaxial compressive strain is applied horizontally. Optimized toughness gave this final design for the initial design used, and optimized compliance approach gave this configuration. So these are tubular structures. And then for shear strain, similarly, tubular structures were obtained. So in summary, this paper presents elastoplastic topology optimization framework. It was analytically derived, and elastoplasticity was accounted for, and the solution was obtained using end compliance and toughness. And the following methods were used. I acknowledge the support of National Science Foundation. We acknowledge the support of National Science Foundation. I thank you for your attention, and we'll be glad to answer questions. And or you can also reach each one of us with the contact information provided.
Thank you so much, Dr. Jasyuk. So we probably have 30 seconds, maybe a minute here, just quickly for some questions. And you can continue to write your questions in the chat. We can come back to them at the end as well. So if anyone has something they want to add right here, we can quickly address that. I have, while we're waiting, in case something comes up with chat, I wanted to ask, why did you choose in the end, after you just looked at the influence of the location of the passive elements, the initial design, the passive ones at the center to as the mode for the rest of the study?
Well, this is a study. This is still an open problem. So we identified that there is a dependence on the initial configurations. The next steps would be to explore these various configurations obtained using these different initial designs and carry it further with further computations and experiments.
Wonderful. There's another question in the chat. Quickly, and while we're answering this, could you stop sharing your screen? And
Yes.
Dr. Topology, if you could start sharing yours and get prepared. So while that transition is going on, we have a question in the chat. Do you also use uniform element densities as initial design?
Thank you. Can I start?
Dr. Jasyuk is quickly going to answer this question, and then I'll have you, Piotr, go next.
Yes, that's correct.
Okay, wonderful. So we have Dr. Topology from the Institute of Fundamental Technological Research of the Polish Academy of Sciences. Thank you so much for joining us. Take it away.
Can you see the presentation correctly?
Yes.
Okay. Presentation I would like to present today is entitled Topology Optimization of Elastoplastic Structures under Reliability Constraint, First Order Approach. After a few words about motivation, I would like to present methodology of topology optimization, reliability analysis, and then I will present some details of our algorithm together with implementation in object-oriented way. And finally, I will present some numerical examples. The motivation is that during the topology optimization process is based on material removal. So it's getting lighter and also getting less reliable. That's why, in my opinion, it is a good idea to control reliability, safety during optimization problem. Our goal is to design a structure. At the start point, there is a design domain with elastoplastic continuum, and we would like to design structure providing that probability of failure is not less than certain prescribed value. Of course, if reliability, it means that there are some parameters which are random nature. In our case, it is load. Our algorithm is similar to SIMP. Design variables are densities together with penalization, of course, and goal is to find density that minimizing volume, providing that structure is in equilibrium state and reliability is not exceed certain level, which allows us to control reliability. As I said, we would like to compute probability of failure. Failure is introduced similarly like inequality constraints in optimization. It's just the function which has negative values in failure zone and positive values in failure domain. In optimization failure, it is called infeasible, as we remember, but reliability has the different name. To obtain this probability of failure, we have to compute integral over joint probabilistic distribution depicted here in the form of contour plot. Here is maximum value. This is the bell-shaped function view from the top. Yes, mean point value and rounding in some distance is equal to 0. Of course, performance function is implicit. We cannot compute this integral directly. So there is approximate method, for me one of the most effective first order reliability approach. We can see two things. Integral over this failure region, mostly this part contributing in this integral because this Bell function here is almost 0. This is one thing. And to design safe structure, probability of failure, it have to be very low because structure have to be reliable. So approximation through the line of this border line, it is enough, and then we have to we can easily compute probability of failure as a cumulative distribution function of distance from the origin. Closest point, called most probable point, To obtain this point, we have to solve optimization problem, minimize distance, providing it lies of these border lines with equality constant. But this is simple because there is iterative formula, and we can obtain it with, I don't know, some 10 iterations. Our optimization algorithm is double loop algorithm. Outer loop, this is optimization, and inner reliability assessment loop, searching for design point. At the beginning of outer loop, we have to estimate, we have to compute reliability together with stress field. Instead of sensitivities, we compute stress intensities. It is average value of Huber-Mises stress divided by yield stress. So it is between 0 and 1, because in plasticity there is no possibility to have stress larger than yield stress. Yes, of course, Gaussian filter is applied to avoid checkerboard effect, and if structure is reliable enough, we can do some evolution of density and next step. If not, we finish our algorithm. Plastic formulation, it is plasticity without hardening based on associative flow rule, computed by finite element Newton-Raphson iteration. At each step there is a increment of displacement computed, trial stress and trial strain. And of course, if trial stress exceeding flow surface, it is impossible, impermissible in plasticity. It has to be projected according to Prandtl-Rose vector into the flow surface. Of course, this approach makes that we have to be careful with load, because we can exceed capacity of the structure. It is important. I would like to present some aspect of implementation, important and interesting for me. We have even some papers on this. Object-oriented allows us to cope with complexity. We can design and implement general structure of data with those code which is common from specific problems, and object which is related to those specific, like elasticity. For example, global matrix is common for all finite element problems, can be implemented once here, and some specific problems, for example, tangent element matrix or stiffness matrix, can be implemented in those specific classes. It facilitates extension problem. We can easily add new elements, new analysis, etc. Of course, if you are a fan of very simple 99-line codes, forget about object-oriented approach. Okay, let's present some numerical examples. First is benchmark problems with force acting at the angle. Solution is two bars at another angle different. Relation between two angles was derived by Rosvani and Mau. There is this analytical solution. As we can see, our solution is in good agreement. Of course, this is elastic solution because I haven't found any benchmark solution analytical for plane stress plasticity. Second numerical example is cantilever with two deterministic force and one force probabilistic. There is a four solution. In first row there is deterministic solution, solution with reliability. First column it is elastic solution. Second column solution with plasticity. This picture illustrates illustrates our idea. If there is a solution without reliability, it is usually optimal but close to the infeasible region. That's why reliability index is less than prescribed threshold, prescribed value of beta index. With reliability, we can control this distance from the infeasible region, and in this case, design structure which is more reliable with reliability index equal 3 as much. Of course, we pay that is heavier, volume fraction is bigger. This is the price we have to pay for more reliable structures. There is some few snapshots from during optimization process at the beginning, more than less in the middle, and at the end of the optimization process. We're observing this decreasing value of volume fraction together with decreasing value of beta sensitivity. Of course, at the beginning, design domain is very reliable. It is obvious. And finally, second example, the similar but design space is different, well-known L-shape example with two forces. One is probabilistic and one deterministic, and also we have seen the same relation. Yes, more heavier is structure with reliability and plasticity. Okay, and conclusion is that the first order reliability is very efficient in connection with topology optimization because it is not very time consuming and can be used as reliability assessment during optimization process. And at the end, our future plans, it is low cycle fatigue, reliability constraints, and it is actually done. What is also our future plans, automatic differentiation, as we can see, or excellent presentation of previous differentiation and sensitivity analysis is very time-consuming process. So I hope that automatic differentiation can facilitate this. Of course, sensitivities are much better than these stress intensities we use. And another future plans is machine learning, because another project we are playing with machine learning. There are some papers I have on my desk with machine learning applied in topology optimization. So I hope that it would be good to use this. There are authors, and I would like to thank the National Research Development and Innovative Office, which supporting this joint grant of the Hungarian and the Polish Academy of Sciences. Thank you for your attention.
Hey, thank you. We have a little bit of time for questions. So again, if you have questions come up, you can continue to write them in chat, and we'll
okay.
Get your question addressed. Just to start us off, two questions actually I have. One is, this may be a bit naive, but can you also start with the outer loop being the reliability and the inner loop in a double loop formulation that you've applied be the topology optimization? If you have an initial guess, is there a reason? What are reasons for having reliability in the center?
Excuse me, what?
You use a double loop.
Yes, double loop. First loop is optimization, and inside is reliability loop. Yes.
If you start with an initial guess, can you do the reliability in the outer loop and then the optimization in the middle, the topology optimization in the inner loop?
Yes, to change in the middle. Of course, there are some even single loop approach, but I think it is very, yes, it is. We can try it because it can facilitate this process, but now, no, I don't consider this.
Okay.
But you are right, of course it's possible, yes. Mm-hmm.
Okay, just wondering about the pros and cons of that. And then the second question, well, if anyone has other questions, please add them to the chat. Second question is, you mentioned machine learning. Is that to facilitate the elastoplastic analysis or something else?
I don't consider any limitation. It depends. As I mentioned, I have this paper in the desk. It depends what they. But of course, my goal is improve this low cycle fatigue, and I would like to do high cycle fatigue. And mostly, I hope that it will facilitate to do something in this branch.
Okay, thank you. So again, as maybe your questions are still coming to mind, please continue to write them in chat. We'll come back to them at the end. So if you could stop sharing screen, Piotr, and then Mathilde, bring your slides up. Okay, so Dr. Boissier is most recently from École Polytechnique in France, but as you see on her slide, now in Grenoble. Take it away.
All right. Thank you very much for inviting me to present this work that I have done at Lehigh University with Natasha Vermaak. And it is about how to do some shape optimization under a shakedown constraint. So maybe just some context about that to explain what shakedown is. So that's a classic shape optimization problem in which we are considering an object that we want to design. We fix part of the boundary, and then we have a load on another part of the boundary. And this load is actually a cyclic load. So basically we're pulling and releasing and pulling and releasing. And the load is going from 0 to a maximum load. And so we want to design, the material is fixed, the loading is fixed, and we want to design the object so that it has a correct behavior. And by correct behavior, we mean that we want to be able to cycle several times without having any damage in the object that we have designed. The first thing we can do is we can choose to have an elastic behavior. That's the one we have here. So basically, when we pull and we release, we would have no irreversible strain, so no plasticity, and so that we make sure that we can cycle several times. But as you see on the Brie diagram, the elastic zone is actually quite small, and maybe if we want to build some objects that would be lighter or with less material, it would be very nice to be able to do something else, to have a bigger admissible space, and so that, but still with a good behavior. And actually there is Shakedown that provides this. And in Shakedown, on the first cycles, you will have some irreversible strains. So basically you will have some plasticity will occur, but then after some cycles, the object you have get back into an elastic behavior. And then, you have still, you can still cycle several times without having any damage trouble. And you see that the elastic behavior is actually a particular case for Shakedown. So when you try to design under a shakedown constraint, the admissible space is actually bigger than it would be for elasticity. And maybe you can get some objects that need less material and these kind of things. So that's the objective here. And just to get used to the notations and explain a bit more about what I have done, I will start by optimizing under only an elastic, to remain in the elastic domain at first. So we have an object, we have our test case here, and then we have a linear elasticity equation that gives the elastic stress. And we know that the actual stress occurring in the object is not exactly the elastic stress. It is the elastic stress when the von Mises function of this stress remains under a yield stress, but then it is a stress so that the von Mises function of this stress is the yield stress. So for example, in 2 dimensions here, you see that at first you have the actual stress and the elastic stress are the same. And then when it reaches the boundary of the elastic domain, the elastic stress is different from the actual stress, which remains on the boundary here. So now what do we want to do? We want to optimize to avoid any plastic strain that to occur in the object we are building. So we want to optimize volume and compliance so that at each point in the object we're designing, the elastic stress remains in the elastic domain so that its von Mises function is smaller than the yield stress. And that is a kind of a classic optimization problem that has been widely studied. We have here chosen a very simple approach to solve this because we wanted to focus on shakedown. Because we want to optimize with respect to the shape, but we know how to do this. We have a partial differential constraint here to define the elastic stress, but we know how to deal with it using an adjoint method. And the only thing that we have to take care is the fact that the constraint is pointwise. So at each point in the domain, in the object we're building, we want this constraint to be satisfied. And to deal with this, we have chosen very simple. We have chosen one approach that was easy to implement, which is to, aggregate all the constraints by integrating over the shape we're building and penalizing where the von Mises function of the elastic stress gets too big. And so now we have, an optimization, an objective function, which is volume and compliance with only one constraint. And we deal with this using an augmented Lagrangian method. And then using a level set method, we can, set an algorithm to optimize the shape. And so here are some first results. So you have the the test case is here, and then the initialization is here. We have chosen one material. Well, the details are not here, but that's the same material for all the test cases in this presentation. And on the first column, we have decided to optimize only volume and compliance without any consideration of plasticity or other constraints. And you see that the volume is finally very small because, well, since you don't put any other constraints, you can remove as much material as you want. But if you compute the elastic stress that corresponds to this figure, you see that it's very high in the middle and in these corners. And it's actually, well, the von Mises function of this elastic stress is actually higher. It's getting out of the elastic domain. And when you add the non-plasticity constraints, you see that the bars are getting thicker. But on the other hand, you are, the von Mises function of the elastic stress is lower than before. And so you are you don't have any plasticity or these kind of deformations that might result into low cycle fatigue behaviors. So that was for the first part, but now, oh no, I'm sorry, I forgot this test case. So we have also the L bracket, which is another test case. So you see that the problem for the L brackets is that we have a very high elastic stress in the corner here. And when you optimize adding the von Mises constraint, you see that the algorithm removes here some materials so that it avoids these very high stresses. Yeah, now we can go to Shakedown. So Shakedown is a bit different, and that is another intuitive way of seeing Shakedown. So we said before that when we load, at first the elastic stress and the actual stress are the same, but then at one point we are getting out of the elastic domain. So the elastic stress gets different from the actual stress, which remains on the boundary of the elastic domain. And then we unload, and we see that if we unload from here, we end here. So we have a residual stress rho that is in the elastic domain. And if we load again, we see that we will start from rho and then load again and remain in the circle. And we see that loading and unloading, we will always remain in the circle. So after one cycle in which we have had some plasticity, then we're back in an elasticity behavior. So we have shakedown, and we know that we can cycle several times without damaging the object. And another case on the right is where you don't have shakedown because you're going that's too strong, and the rho is not in the elastic domain. And basically, you know that here, when you unload, you will have some plastification, and when you load again some plastification, and so on and so on. And so here, after some cycles, your object might be broken. So that's what we want to do. But the way I have explained this to you is by using the loading history. And that is something that we cannot do in shape optimization because we don't want to compute the stresses and plasticity every time we are trying to optimize. And this is where we have a very nice tool, which is a theorem that says that we know a structure will shake down if there exists a stress satisfying the fact that this stress is in the elastic domain. So that's what we saw before. The rho arrow was, maybe I can go back. The rho arrow is in the circle. And also the fact that rho plus the maximum, the elastic stress corresponding to the maximum loading is in the circle. So that's what we saw here. The rho plus the elastic stress is just here, so it remains in the circle. So that's good, we're in the elastic domain. And also this stress must be self-equilibrated because of course, when we're unloading, we're removing all the loading from the object. And so this stress has to satisfy this equation that corresponds to, well, to the equations a stress must satisfy when there is no loading. And now we want to optimize with this. So before we're optimizing the shape, and now we decide that the it exists constraint is transformed into a two variables optimization. We optimize the shape and also the stress, assuming that if we find both at the same time, then it means that the shape will actually satisfy shakedown. So we still optimize volume and compliance. We have these constraints coming from the pointwise constraints are transformed to, well, aggregated constraints for the fact that rho is in the elastic domain and rho plus the elastic stress is also in the elastic domain. We have the self-equilibrated equation and then the linear elasticity equation. Well, we still have one trouble, which is the fact that this equation, we don't have unicity, a unique solution, because we don't have anything on the Dirichlet boundary condition. We don't have any Dirichlet boundary condition. So we have to find a way to, well, express this constraint another way. And something that is very nice too here is the fact that the space of stress can be, well, we have is in direct sum between, well, self-equilibrated space is in direct sum with this complementary space, which is very nice. And so it is very easy to characterize the projection of any stress on the self-equilibrated space. So the constraint of being a self-equilibrated stress is dealt with by actually projecting onto the space, which brings a new optimization problem, which is the last one. We have volume and compliance. We have both constraints. We see here that we don't have directly rho. Well, actually, this is rho, but we're looking for a stress. And here we are considering the projection of this stress onto the self-equilibrated space, here and here. And we still have the linear elasticity equation. And then here is to compute the projection of the residual stress, of the stress onto the self-equilibrated space. So we can apply the very classic adjoint method techniques and then also shape differentiation techniques. And here are the results. So that's the cantilever we had before. Here it's ideal elasticity. So that's what we said. Very thin bars, but we have some trouble with plasticity. When we consider von Mises constraints, so we don't want any plasticity here. We see that the bars are thicker. And well, we remove plasticity. And then when we consider shakedown, we see that the volume is actually between the volume for ideal elasticity and volume when we want to avoid plasticity, which is quite logical because we increased the admissible space by considering shakedown instead of no plasticity. And then we have a residual stress that is, well, that appears. And we see that both stresses remain in the elastic domain, which is correct. And same kind of results for the L brackets, in which the volume ends up between the volume for ideal elasticity and the volume for no plasticity. And we see that we still have removed here the red part saying that we had gone too far to remain, well, to have no classification. So basically here, we see that we will have a high cycle fatigue behavior, which is what we wanted at first. Well, here is the articles that correspond to this. In there are more details. And I thank you very much for your attention, and I will be pleased to answer questions.
Thank you so much, Mathilde. So no questions in the chat yet, but please go ahead and put your questions in the chat while we're waiting. I have one to start off, and as you noted in the presentation, the shakedown solution is always in between the ideal. Oh, we do have one. I'm going to get that one first. Have you thought about testing the Armstrong-Frederick kinematic hardening?
I started to look at it, but then I had no time for this, so I have not gone further at this point. But I think, yeah, I think there's still, I forgot to put some perspectives, but there are still several things to do because having shakedown is only the first step. And then I think you can do more, well, a lot more than this.
Okay, so while we're transitioning, oh, they also comment, nice work.
Oh, thanks.
Dr. Wall. So let's have the next speaker bring up their slides. So we're transitioning to Dr. Feisman. And you can, again, please put your questions in the chat and we'll come back to them. So Dr. Weissman is from Columbia University in the US, and I thank you for presenting and joining us today. Take it away.
Thank you very much, Natasha, for the invitation. I'd like to present topology optimization for elastoplastic analysis that also include local ductile failure constraint and linear buckling analysis. But before I will start, I wanted to acknowledge the contribution of my former student, Jonathan Russ, who has done most of the work on this paper, and currently he is in Princeton doing a postdoc. Okay, so my talk is going to discuss the following. First, I'm going to present a motivation to the problem that we are solving. I'll present the mathematical statement and optimization problem. I'll talk a little bit about calibration, material calibration, show some numerical examples, and conclude the discussion. You can find more details, of course, in this paper that has been recently published. Okay, so let's start from this example. Suppose that we want to optimize this cantilever beam, aluminum beam, and let's say that we want to maximize the total work under some mass constraint, right? So we will use FEM-based topology optimization. We will discretize the domain. Every element is a design variable using a standard SIM method, and we arrive at the following optimal structure, right? But now this is where things get different, right? Now we want to apply this optimal topology to a verification step, right? So now we want to try to test it in kind of the real world. So apply it under large strain or finite deformation ductile fracture model and see what is happening. So if we apply that to this finite deformation theory, we observe that the following behavior. We observe that on the left side, we will have the plasticity is indicated. You can see there is some localized plastic deformation in certain regions. On the other side, on the right side, we are looking at fracture. Again, in this case, we are solving it using a phase field method. And so we see that there is no fracture, actually, because everything remains blue. But what we observe is that we have buckling of members that happen, right? So actually, when we are interested in failure and we are applying a large deformation theory, it can fail by buckling before it actually fails due to plasticity. Right, and so this is our exactly goal, right? The goal is to kind of find an topology optimization such that we will increase the strength of the material or the peak load, and also increase the ductility or the structural toughness of the material. Now, just to mention literature review, I cannot review here all the literature, but people have worked on elastoplastic analysis, buckling, and failure problems, but they have not worked essentially on including all of them in one topology optimization. So this is exactly where we are coming in. We want to kind of include both buckling and ductile failure constraint in one optimization in a simplistic or simple way. So what is our general approach? Our general approach will be the following, right? First, we will use FEM based on the SIMP method. The forward problem will be solved using a small strain J2 plasticity model. And then we will incorporate the buckling analysis and ductile failure constraint in the optimization. Those will be incorporated as an aggregate objective function, including both the total work, the buckling, and fracture constraint. We will then use the adjoint method with pest dependence, as has been discussed in previous talks here. And then once we converge, we're going to apply a finite strain ductile phase field method to actually verify or test whether this topology is good or not. So in terms of the mathematical statement, the problem can be described as follows. We have an aggregate objective function. So we want to maximize the total work, right? Or have more ductility essentially under some mass constraint. In addition, we will have kind of local ductile failure constraint imposed at every quadrature point or every Gauss point. And the fourth problem will be solved using a J2 plasticity elastoplastic analysis. Just to mention that we will use an augmented Lagrangian technique developed by Senora et al. To impose those constraints. Those can be viewed as just indicators that cannot reach a certain level or one in this case. This is known as a Johnson-Cook failure criteria in general. Here we have D1, D2, D3 are coefficients that are calibrated depending on the material that's used. And then NQ is the stress to axiality that is obtained. Now, in addition, we will have in parallel a buckling analysis shown in blue here, where we will solve a linear elastic buckling analysis, essentially following Ferrari and Zygmunt approach for buckling. But this linear elastic step, which will be run in parallel, will be added as another aggregate, another function into your aggregate objective function using this KS function described in Ferrari and Zygmunt. So in this way, we will have both buckling and ductile failure constraint at the same time. So let me just illustrate kind of the procedure, right? This is the optimization scheme, which if we neglect the outer loop here, will be kind of similar to what has been presented before. So initially we have kind of filtering and projection steps, which are standard. So I'm not gonna present it. You can find it in the paper. This kind of branch is the elastoplastic analysis, where we try to maximize total work, right? We wanna have as much ductility as possible. But in addition, we will have these ductile failure constraints, which are added as an augmented Lagrangian into our optimization. At the same time, right, there is another branch here, shown here, which would be the linear elastic buckling analysis, right? So essentially for every realization of, or every iteration that we have a candidate topology, this candidate topology will be subjected now to a linear elastic buckling or kind of an eigenvalue problem, and using the first few modes and buckling modes as well, the buckling load factors and buckling mode shapes, this will be fed back into the optimization, and we will be also taken into account. Now, I wanted to emphasize here that we have seen the path-dependent topology optimization discussed in previous talks using the adjoint method. One thing I wanted to emphasize, I'm not sure if people are aware, but essentially these operations can be done at the element level, because Gauss points are essentially decoupled from each other. And so you could do some of those operations at the element level and have significant savings in the calculation of how this is done. This is also in the paper if someone is interested in this. And so once we are done with and we obtain an optimal topology, then essentially we will subject it to a large strain finite deformation to test whether this topology is actually the best one or not. So let me go into a little bit details here. First of all, the small strain J2 plasticity model. We have here a nonlinear hardening law. We have kind of, as people discussed in previous talks, we have global residual equation. We have local residual equation at Gauss points. Here, nothing is special, right? We will run a return mapping algorithm at every Gauss point to come back to the yield surface, as noted before. One thing I wanted to mention is that we're using this Vogt type hardening law, which essentially have kind of a saturation or very long ductility, which is typical for aluminum. In terms of the buckling analysis, as I mentioned, for a given candidate or for a given iterations, right, we will solve a generalized eigenvalue problem to find the first buckling modes and then add those as an aggregate function using this BKS. So essentially here, there's nothing essentially new, and it follows the same procedure in Ferrari and Zygmunt. And then finally, the ductile failure constraints. So we have this Johnson-Cook model that is shown here. Those parameters are can reach up to 1, from 0 to 1. D1, D3 are parameters that needs to also be calibrated from real experiment, and NQ is the stress to axiality. The augmented Lagrangian approach, as noted in this paper by Sinora below, is used here to augment this constraint into our objective functions. However, I just wanted to mention a small feature here. The original paper proposed these functions that could be used. And in this paper, we have a slight modification. We introduced additional 2 parameters that basically gives our functions not to be a 0 function, right? So then you can compute sensitivities and the procedure can converge faster with those additional parameters. Then let me just mention briefly the calibration, right? So in order to study that, we had to go and really calibrate a ductile fracture model under large deformations. So you can see here this bar, 12 millimeter radius bar, and there were other bars that were available in this paper by Bao and Wierzbicki from MIT. You see the black line in the force displacement curve indicates the experiment, and the red curve indicates the phase field fracture model that was used to calibrate those. We also had to calibrate the ductile failure constraints, but I don't have time to show it here, but this is also had to be done to get that. Okay, so now let me go into some numerical results. So now suppose that now I'm going back to this optimal design of a cantilever bar. And here the notation is the following. W is the design where I neglect both ductile failure constraints and also buckling analysis. WF is where I omit buckling. So I have only the ductile failure constraint and the total work. You can see that here the optimizer tried to reinforce the part that is in tension more compared to the one that is in compression. Then we have the total work together with buckling, omitting ductile fracture. This is the design. And then finally, we have all 3 of them as I presented, and we have the following design. So how do we know which one is better? We go and we test it using that phase field large strain method, right? And if we test that, this is what we get. So we see that like these are the structures that are obtained using this optimization. What we observe is that the first row is essentially failure due to buckling. But you see that there are members that buckle because we have not imposed any buckling constraint. On the other hand, if we impose the buckling constraint in the second row, we will see that failure will essentially occur due to fracture. You can see here that we have fracture. So which one is actually better? We have to draw or look at the force displacement curves. And what do we see? We see the following 4 different designs. We see that the best design is noted by the green point, and this includes both the buckling and failure constraint. And what's interesting is that we can increase the peak load or strength of the material by about 15% and almost 900% increase in ductility, which is very, very important for applications such as energy dissipation and so on, that you want to increase ductility as much as possible. Another example is this portal frame example. Again, we have
1 or 2 minutes left, just a quick.
Sorry?
1 or 2 minutes left.
Yes, so I'm fast. I have the same design for the portal frame. I have the 4 different designs. And again, these are the results, again, due to failure due to buckling, failure due to fracture. Again, we see the same force displacement curves where we increase the peak load by almost 5% and the total work by 270%. And then finally, I just wanted to show here this movie that shows how we take a candidate design and subject it now to a large phase field ductile fracture to test it. You can see the fracture initiated and propagates essentially as a mode 1 fracture. Okay, so with this, I will conclude my presentation. We have demonstrated an approach that can include both ductile failure constraint and buckling analysis in a simple way into elastoplastic design optimization. And we have showed the importance of having this verification step, kind of the real world, subjecting your optimized design to the real world scenario and demonstrate good results. I'll conclude by saying there are much more to do with failure and topology optimization, and you're welcome to look at this paper when you have time. Thank you very much.
Thank you so much, Dr. Wesson. We have a few questions. So first one is, did you observe any artificial buckling modes in void regions?
I don't think we observed that.
Okay. Second, they praised great presentation first, and then question, how do you choose the values of the weights W1, W2, and W3 for the terms of the objective function, and how dependent is the solution on the choice of these weights?
This is a very important and key question. It's actually some sort of an art how you choose that. In our work, we have put 80% for the total work, about 20% for buckling, and then kind of 1% to the ductile failure constraints. But in general, yes, this would be dependent on how you choose those parameters. But for those kind of parameters that we choose, if we shift a little bit, that we haven't seen much of difference in the design in this case. But this is really a key question. Yeah, thank you.
Thank you so much. So I'm going to have you stop sharing. The next presenter is Dr. Balin. Bring up the slides. And then just so you know, you had another question. So if you can answer it in the chat, otherwise we'll come back to it at the very end. Okay, so our last speaker today is Dr. Balin from Lund University, LTH in Sweden. Thank you so much for joining us. Take it away.
So thank you. Can you hear can you see my slides? I had problems before.
You're great.
Perfect. Thank you. Yeah, so today I will talk about plastic work constraint topology optimization, and most of this work has been done by my former PhD student, Niklas Ivarsson, and I will also acknowledge my co-workers, Ude Rameh from Haifa and Dan Tortorelli from Lawrence Livermore. So my talk today will actually be about two papers. So you have seen a lot about plasticity and topology optimization, so I will continue along those lines, but I will also show you a little bit what we have done to handle boundary effects if you go if you have random corners. So of course, as you have seen, we are not the first one by any means. I will just show you that it started off already in 1998 by Kurt Maute. He did a little bit of topology optimization and compared elastic to plastic designs. And a few years later, Klaus Pedersen, he did kind of crashworthiness analysis. And then there was a lot of work in between, but we did something in 2016 where we had finite strain and plasticity. That was extended a couple of years later where we included dynamics. So in this example, you have a double clamp beam. If you apply the boundary conditions really, really fast, you will lose connections to the boundaries. So the optimal energy absorption will be in this kind of weird design. And then if you do this slower, you get more and more connections to the rigid walls. And of course, you can apply exactly the same framework to material design. So we use this to design a microstructure. So this is biaxial loading and also energy absorption. And that is kind of an observation in the literature that most work on topology optimization and plasticity has been done on maximizing the plastic evolution for energy absorption application. One exception, of course, there are several exceptions, but one exception is the work done by Ude Rameh. So he took a elastoplastic model to use that as a way to do stress optimization. So if you can guarantee that you have no plastic strains, then of course you know that you have fulfilled the yield conditions. So your effective stress is below the yield stress. So that is kind of similar to what we are doing. Even though in this work, we will allow a certain amount of plastic work to be done in our structure. The model we make use of is, it's finite strain plasticity, but it's the most simple model that you can come up with. So we make use of a multiplicative split of the deformation gradient instead of the additive split of the strain tensor, small strain tensor. We use finger tensor and isochoric finger tensor. We use total Lagrangian setting and a very simple Neo-Hookean model for the elasticity. And the yield surface is just as you have seen previously, a von Mises type of yield surface. So this is the yield, the normal to the yield surface in stress space. And we have isotropic hardening. So this guy here, that can increase, which then will increase the radius of the yield surface. And the increase of the radius of the yield surface is governed by this scalar variable, alpha, and this is the evolution of that one. So lambda is the plastic multiplier. And if you're not familiar with large deformation, you can just think of this guy here. This looks slightly weird, but this is just the plastic strain rate. So you can see that n is the normal to the yield surface, which you might recognize, and then you have the plastic multiplier. So forget about the rest of the junk in this equation. We integrate this equation, these two evolution equations, using Beck-Reuter scheme. We could have used an exponential update, but in this case, we used a Beck-Reuter scheme. So in each Gauss point, we will have a set of equations. So that one is a tensor equation, so 6 equation in this case, plus another one to fulfill the yield condition. So in each Gauss point, we need to solve a set of equation, and the unknown is we collect them in this V vector, and this C vector contains both these two residuals. So that should be solved in each Gauss point, and with slight abuse of notation, we gather all these C in Gauss points into a large one, a C, which then includes all the Gauss points. So that is what we need to solve independently. If you would like to use, for instance, as we talked about previously, you might want to use a kinematic hardening, for instance, the Armstrong-Frederick law. The only thing you need to change is in this local guy here. We use finite element to solve our balance equation, and of course consistent tangents to preserve a quadratic convergence in our Newton iterations. So that is what we are faced with. And the problem is, in this case, we have already talked about this, so maybe I can just go through it fast. We have a path-dependent material, so if you load it in actual strain, shear or load it in actual strain, or if you shear and then load it, you will end up in different endpoints. And of course, if the state problem is path dependent, then the sensitivity will be path dependent too. And nowadays, this is kind of well known how to handle this. We have a fairly general objective cost function, could be constraint functions too. We have the state variables, in this case, the elastic finger tensor, and our isotropic hardening variable. So they can be included in all time steps. And we have the standard machinery. So we add to get rid of the implicit derivatives. We have the adjoints for the residual equation. We have adjoints for our constitutive equation. And the way to solve this is to solve our state problem in this way. You just ramp up the load. And then when you have solved the problem, you can go backwards in time again. So this is well known, and nowadays it's out there in many papers. And it was published already in '94 how to solve this problem. So now to the second paper I would like to advertise in this talk. So since we are doing minimization of plastic work, we have the constraint on the plastic work. It will be quite similar to stress optimization. And we all know that if we have a stress concentration along the boundary, we will have to do a trick. We need to do something at the boundary in order to avoid weird effects at the boundary. And so in this slide, I will show you how you can do that with a PD filter. So the filtration we do in our paper is based on the PD filter proposed by Ole Sigmund and Bojan Lasov a couple of years ago. And they solved this equation together with these boundary conditions. And it turns out you can put these two together in a potential. So minimizing this guy here results in this boundary condition and this strong form. And here you can see that this PD filter, then if you make this interpretation, you can see that the PD filter actually a competition between two terms. You have this term and the second term. So the MMA will tell you that you should go with the raw if you use the gradient-based optimizer, MMA method moving asymptote. So you will have this one if you ignore that one. So if you minimize this potential, raw will be equal to raw tilde. But now we don't want to have this piecewise constant design. We would like to smooth our design, so therefore we add this extra term. Actually, Bojan and Sigmund did that. And If we increase this, we will get a smoother and smoother design. The problem is that, but if you have designs along the boundary, there would not be a penalization of the design at the boundary. And that is well known. So if you just run this example, you will get designs like this. You will have a sticking effect. The design will try to be close to the boundary. If it's near the boundary, it will try to attach to the boundary. It will also have these perpendicular designs towards the boundary. And this example, I think this is from my old paper in phase field. We have exactly the same problem, and padding techniques was discussed, and this effect was also discussed in this paper and in the one I would like to advertise at this point. So the way to solve this is to add an extra term. We simply say now we have a cost for having designs at the boundary too. So if rho is equal to 0, there is no cost, but if rho is equal to 1, now we have a cost for having designs at the boundary. So if we add this term to the already stated terms. And if we do that and minimize this potential, we will see that we'll get this boundary condition instead of having a 0 here. So instead of having a homogeneous boundary condition, now we will have a mixed boundary condition, a Robin boundary condition with a new length scale. The problem is that we need to find this LS, so we need to relate this new length scale to this L naught. And we did that by just comparing these designs. So now I have two different ways of handling my boundary. So this is my 1D boundary with padding. Now I have my design without padding, and I would like the design to be exactly the same. The filter density should be the same in this region as in this region. And if I just solve this 1D PD, it's a differential equation, I can identify my length scale, this guy here, to that one. And it turns out that they should actually be the same. And then you have the same slope here of the design, and you have the same value of the design at the boundary. So that's an easier, and it turns out to be extremely simple to implement. The only thing you have to do if you have implemented a PD filter, you have to add one matrix, and that is, you don't have to do any padding at all if you're doing like in this approach. And it turns out that you can get very nice designs. So without the length scale, you will get the sticking. It will try to attach to the boundary. And if you add this LS equal to L naught, you will see that now there's no sticking effect left. Okay, so now to the problem that the elastoplastic problem. So we do minimization of end compliance, and it's well vaguely motivated to low cycle fatigue, since you do allow a certain amount of plasticity for low cycle fatigue. We have in all examples a volume constraint 35%, and then we take the P norm in order to pick the maximum plastic work, and P is equal to 8 in this case. So you can see that we look at each Gauss point throughout the structure, raise that to the power P, and I can see that there's a D, well, yeah. And then we have a constraint on this guy. We allow a certain amount of plasticity in the maximum peak plasticity in the structure. Material interpolation turns out to be kind of critical. In this case, we use exactly the same P exponent, simp exponent, for both the yield stress and the elasticity. We haven't done that before. When we did energy maximization, we have the P for the yield stress slightly lower than the elasticity. And we use this augmented filter that I just showed you, and some standard techniques, heaviside thresholding with beta is equal to 10 at the end state. So one well-known example, we have seen it today. It's an L-beam. We load it, displacement control, and with a constraint on the plastic works. And of course, it will be quite similar to a stress optimization. You have seen this kind of design in many other papers. I would just like to show you the effect of this padding procedure or this filtering technique. So if you don't include this LS, if you put that equal to 0, you will see that you will get this kind of weird effect at this border, this boundary here. You will see that the design tries to align with the boundary. But if you include this LS equal to L naught, then you see that you get a nice and smooth design around the re-entering corner. So this is kind of, if you have this one, you will get weird stress distribution around the corner. Another advantage of this, of including plasticity, is that now you can actually handle a path dependence. And in this case, just to illustrate, you take this, basically it's kind of a torque. You apply you displace U this side and this side. So you do that simultaneously in this way. You will see that you get a fairly symmetric design. But if you in this case take U1, you clamp this one for a while, and then pull this one, and then delay the motion of this point slightly, and then when you are halfway, you increase both so that you end up in exactly the same end state. And here you can clearly see the difference. So if you have this kind of, you have the same, if you have a linear elastic or if you have a hyperelastic model, you will not see that you will have different design. It will be the same if you don't have the plasticity. And in particular in this region, you have a huge difference. Here you have the V-shaped design, whereas here you have a rounded design. So if you cross-check this, that will be a significant difference. I think this is a final example. So it's a double clamp beam. If you have the elastic design, this is also well known. We have seen that in many papers. But now if we allow a certain amount of plasticity, so the peak plasticity value, if we allow that to increase, we can see that the design more and more adapts to the loading. So if we allow quite a bit of plasticity, we see that we get a completely different, it's way far away from the elastic design. So I will wrap up, just concluding remarks. So, well, of course, as Uded showed, we can have the strict zero plasticity constraint can be a stress constraint. And that was not shown in Uded Amir's paper, but now you can handle path dependence. And of course, we show that that can be of significant importance. And the filter I showed you, it removes the need for padding. And I will also say that it's extremely simple to implement. It's just adding one constant matrix, so it comes with basically no cost at all. So I think that's it.
Okay, thank you, Dr. Volin, so much for your presentation. Again, please put questions in the chat. I saw there was quite a robust discussion for the questions that continued from the previous speaker, so please put your questions in. I have one to start off, actually. Something that I thought was fascinating about your paper was how when you had an asymmetric design and then you had a symmetric design and you switched the load cases, and the asymmetric design was robust to both load cases, the one it was actually designed originally for and the one that you switched out on it. Can you talk more about that, what you think is going on?
I think, to be honest, I think it's just a coincidence. I have no explanation why that is the case. We have tried other cases, and I mean, it's hard to see that is really the case. So I will not claim that is a general conclusion at all.
Very good. Another thing that came up was you made an argument about the importance of allowing plasticity in intermediate material regions, and that's kind of in contrast to the current, I don't know, literature and people's stances out there right now. It was important in your case, and you think there's additional information that is important. Is that also a coincidence for the cases, or do you think this should change the direction of the research? And
I mean, we started off by doing the same. So normally you need to have the exponent for the yield stress slightly lower compared to elasticity. But in our experience in this case is that we had to have the same penalty exponents, and then you get this effect of having plasticity in outside. So the sensitivity simply works better in this case. I think that depends on, now we would like to have, if you do energy absorption, you have a lot of plasticity, whereas in this case you have almost no plasticity, but you need sensitivity information. So I think that is my answer to that.
Okay. So then, again, we've come to the end of the presentations, and I have a few questions for all of the speakers, but if you do have additional questions for Dr. Volin, please put them in the chat and we'll record them or get to them as well. So if all the speakers could come back to video, if you're available, and unmute. I want to kick off just a general question for everyone in that, what do you think for inelastic design and topology optimization applied to inelastic design? What do you think any challenges or obstacles or barriers that this community needs to solve to really make more progress in advancing topology optimization for inelastic design? Anything come to mind for you guys?
Well, I can start. I think it's just the world is really complicated. That is my conclusion, that now you get path dependence, and if you include rate effects, you get dependence of rate, and the design space is so great. So it's really a challenge to somehow capture all of the richness of the nature. There's so many variables you can change. So some kind of robustness over all these variables are probably needed, since you see that the designs are completely different if you increase the rate, if you allow wave propagations. So I think we saw one talk on robustness. Maybe that is the way that we need to include.
Mm-hmm. Thank you. Anyone else from the speakers want to chime in?
I think that in addition to path dependence, which is obviously difficult, and you don't have it in other designs, what I'm interested in is in failure processes, right? So for example, fracture, failure, you want to design the structure to kind of to the real world, right? In the real world, we have failure, right? And we have seen several talks here that kind of remove the corners from structures. So in the past, for example, we have done work that includes the physics of damage mechanics and fracture in the optimization. I think that with this, it's much harder, but you can achieve different things that probably you would not be able to achieve without including the physics of failure in addition. So these are some of the challenges that I think in that field of failure.
Very good. Anyone else want to chime in? Okay, so one of the things we noticed is we're still kind of using the L bracket and maybe double L bracket and cantilever, which are well-known, benchmark problems. I'm wondering if you think that there are, for inelastic design, there's opportunity to introduce new kind of case studies that would really highlight the benefits of going beyond purely elastic design in a better way, perhaps.
As far as I know, there are very limited analytical solutions for, let's say, an elastic design. The only one that I'm familiar with has to do with HRR fields. Hodgkinson, and I forgot the rest, I apologize, but they were able to derive analytical solution for HRR fields. But I don't know anything else that has analytical solutions. So I don't know.
And
Maybe.
Dr. Tozowski presented the analytical solution for the two-bar problem in his presentation earlier as well. But yeah, that is a challenge. So given this audience, is there any homework that you would love to assign to this audience, collectively work on in this field, in this application of topology optimization? Is there any homework that you would love to give this community? So we haven't heard from Mathilde or Dr. Jasyuk or Dr. Tozowski, Dr. Boissier.
All right, I can try, but well, I have not done much work in this field, and I think this is not my field anymore. But I think for me, one thing I found the hardest during this work was the computational costs that are so high, and everything gets very, very complicated each time you are considering plasticity. And so I think that maybe there are some ways to make this easier and less less complex, and I guess we can still work on, well, they have been widely developed, but we can still try some new models, a new way to represent things that would make it easier, both in the formulation and the way computer can deal with it, because it's kind of very annoying to wait so much time for each iteration to be computed. So yeah.
Very good.
So along those lines, yeah, I would like to see more three-dimensional analysis that could be, translated eventually to practice.
Very good. Thank you. Fyodor, do you have anything to add for any of the questions I've thrown out? Oh, you're muted.
Actually, I have that impression of question. Is there any place for some probabilistic approach in this inelastic design? I don't know, reliability, maybe robustness, this kind of approach. Thank you. Somebody can answer, or?
Yeah, yes, I absolutely do believe
yes,
that.
Yes.
Because I was unique for who involved probabilistic in this, but I think I wonder if it is just coincidence or there is no place for probabilistic.
Oh, no, to the contrary, I absolutely believe their reliability, probabilistic, non-deterministic approaches are needed, especially because in many industries, designers can be leery of including plasticity or in their design approach. And so having the robust tools to show confidence in the structural response, even beyond the elastic, it's much easier to stay elastic, right? And to enforce elastic response. But there's a lot of richness, a lot of complexity, but a lot of richness and benefit to be derived by doing inelastic design. And so I absolutely think that there's a role, and that's why I was excited to include your paper. Any of the other speakers want to comment on that as well?
I will mention that uncertainty is everywhere, right? I mean, the world is uncertain. So definitely some probabilistic approach that at least provide limits to the designs, right? What is the limit, right? What are the averages and things like that would be definitely useful. So in our world.
Thank you.
Okay, so I don't see any other questions coming in through the chat. So I'm gonna save everyone the last 2 minutes to get to your next meetings. I really appreciate all of the speakers for your time today, for your willingness to present on the recent papers that you published in this topic. I hope that we get to collaborate in person one day again. And thank you also to the organizers of the top webinars. It's been a pleasure. And I think I'll hand it back to June for any other announcements for upcoming webinars and housekeeping.
Natasha, thank you very much for organizing a wonderful session. And also I would like to thank all the speakers for keeping the time and for engaging in a very lively discussion. And also everyone for joining us. Announcement for the next session. Next session will be about wave propagation problems. It will be organized by Professor Rasmus Christensen from DTU Denmark. So the next session will be slightly more than 2 weeks away. So I look forward to meet many of you next time. Bye.
Bye. Thanks.